Well, thank you. It's really a pleasure to be here at Sendai for my first time. And so close to the ILC. Soon. Which is very exciting. So we just heard a comprehensive talk about the state of particle physics, which was somewhat pessimistic. I hope I can be a little more optimistic. And I hope I can provoke some discussion, because that's the purpose of these forums. We are at a very unusual time in elementary particle physics, flushed with success, triumphant in a way, but at the same time depressed at our success and unsure as to what the future will bring. The standard model of elementary particle physics has been amazingly measured and confirmed in across all of the forces and particles that it describes at the LHC in the last few years. Both the theory of the forces in nature and most spectacularly, the added ingredient that we had to put in by hand of an elementary scalar field to account the model in the simplest possible way, the spontaneous symmetry breaking of the weak nuclear force, the so-called Higgs mechanism, or as now denoted by the Nobel Prize Committee, the BH mechanism. This theory that we have, the so-called standard model, is unbelievably successful. And so we should, as a field, elementary particle physics, and as a field of science, physics, and even as just a scientist, be extraordinarily proud of the enormous amount of the success of an enormous amount of experimental discovery and measurement and theory that went into the construction of what should really be called not a model, but a theory. I didn't take the chance to chide Steve Weinberg, who just spoke, for inventing this term, the standard model, which originally was to distinguish SU2 cross U1 theory of electroweak interactions from any other contender, and then was used nowadays to incorporate QCD as well, and really should be called, if anything, the standard theory, or how about the theory? It describes, with a few parameters, in most relevant cases, like understanding the composition of ordinary materials, all observations, just about, and does so with incredible precision, continuing incredible precision, which is amazing, and over an extraordinary range of phenomena. So unbelievably successful that we despair. And most recently, we've verified this, the ugliest part of the standard model, this term that was put in and field just for the sole purpose of explaining how and why the electroweak symmetry breaking is broken. 50 years ago. And that, as we all know, was recently awarded by this year's Nobel Prize to the surviving pioneers. So this is an incredible triumph, but I often say that science thrives on ignorance, which is the product of knowledge, and we're all searching with new knowledge and new tests and for new ignorance. And we have some ignorance, but obviously not enough. So I'm not going to do as Steve did and describe the standard model in great detail, but try to say a few words beyond the standard model. And we do luckily have ignorance and questions, and very interesting questions, that are both experimental and theoretical in their origin. In my opinion, the most urgent, experimentally motivated, observationally motivated question is the nature of dark matter. I mean, there, presumably, is a new particle that was not discovered by particle physicists for the first time. Our friends, the astronomers of all people, have discovered a particle which so far we cannot observe directly in the lab or produce, no matter how much energy we pump into accelerators, or even see direct signals for. We can only observe it indirectly through its effect, gravitational pull on planets and on stars and other galaxies. Neutrino masses, of course, are an experimental observation measurement. Wonderful. How do we don't even know whether the neutrino is a Majorana particle or not, I mean, which is a sort of a scandal after all of these years that we can't decide that all-important question. So there are many many questions and measurements that have yet to be performed and understanding. And then, of course, there is the baryon asymmetry of the universe, which we sort of have understood for many years what the theoretical ingredients for explaining that asymmetry might be, and even the basis of a calculation. The calculations so far don't really work with what we know for the parameters that would go into the calculation. So we need more measurements and better theory. And then, of course, there is the big, most mysterious of all the questions the theorists face, but how to explain the cosmological value of the cosmological constant, which isn't, as we all thought, since we couldn't calculate it, not non-zero. And then there are theoretical indications, which are often taken very seriously now, even by experimentalists, as Hitoshi said, like the hierarchy. Hierarchy is a theoretical question. There is a disparity in scales. This bothers theorists for good reason. It suggests that there must be something more than just a difficult calculation, some principle that's missing. Unification of the forces is something that you don't go ahead and observe directly or measure. That's a theoretical goal, as a rather successful one in the history of physics, and strongly motivated by the standard theory, which has three kinds of gauge interactions that are conceptually the same force, except for there being 1, 2, or 3 different kinds of charges and 3 different forces, cries out to be unified. And then, of course, the theoretical issues of which we are forced to consider, even in particle physics, arising from the great success of quantitative cosmology in recent decades. Now, luckily, for some years we've been in the situation where many of these issues might be approachable at the TeV energy scale, at the LHC, and in particular in the context of ideas about supersymmetry, a beautiful, wonderful extension of the symmetries of space-time, which arose independently and offered a solution to at least 3 of these most vexing problems. And still might work, even though the preliminary indications from the LHC aren't encouraging. The extrapolation of what we do know to what we don't know is something that theorists do. And hopefully we can provide experimentalist guidance as to where to look. And as Steve said in his talk, the fact that now 40 years ago almost, we extrapolated the standard model and discovered that the 3 subatomic, subnuclear forces and even gravity tend to come together in strength at an extraordinarily large scale, has posed the most encouraging challenge of unification for 40 years, but also the biggest conceptual obstacle for observing directly the new physics. Because the Planck scale, or close to it, is where the forces appear to unify. And that problem of the enormous hierarchy between what is probably the fundamental scale, in some sense, of physics and present-day observation, or the limits of observation in the next few centuries, poses an enormous challenge. And we have been hoping that, not to build accelerators that could directly probe the unification scale, but of finding as many clues as we can as to the physics up here by observations down here that could likewise be extrapolated to give us information about the truly new physics. Supersymmetry was indeed, in my opinion, the most exciting of such ideas, which not only made the unification work better quantitatively, but also could provide explanations for both for the actual one of the hierarchies of nature that is hard to understand, the hierarchy between the weak scale and the unification scale, as well as a candidate for dark matter. And all of those clues and others for the usefulness of supersymmetry seem to suggest that supersymmetric particles predicted by any supersymmetric version of the standard theory must appear at around a TeV, and so the LHC was where to look for it. But we must remember, especially since we haven't discovered supersymmetry, that all of these clues could be coincidences. And for those experimentalists among younger people, theory has been very triumphant in the last 40 years, but you should be skeptical, and we, in fundamental physics, the problem is one is always working, or at least in eras which are similar to the current era, with clues and not evidence. and we could all be wrong. Actually, I still have lots of hope that the supersymmetry will be seen, I hope soon, at the LHC. But it could be, and that we've just been barking up the wrong tree, and we or young people should not take so seriously these ideas. Try to think of alternatives. It's not easy. But from an experimental point of view, and one thing that is clearly dictated by this picture, with this enormous gap in energies between where we perform experiments nowadays and where all indications of higher scales where new physics might arise, is that we must fully and totally explore the energy range into which we have started to explore the LHC. And that's why it's so important to start planning the efforts that go beyond it now, such as the International Linear Collider, or CLIC, or other large machines at CERN, or a large accelerator that would use the Tevatron as a booster. Of course, here in Sendai, in Japan, the focus has been on the ILC, and I am extraordinarily happy that Japan is taking the initiative to lead the effort and to construct this collider and to help fully explore the TV domain. So this is really important, and it will be important also to begin starting to plan a huge hadron collider or very large hadron collider either in Geneva or Texas or China or somewhere. We have to make sure that we don't miss whatever clues and new physics is available in the TV range, because the stakes are so high if we do. And the future is unclear. One way of describing this is to give two extreme scenarios: the optimistic scenario and the pessimistic scenario. Now, I am by nature an optimist, and I think most physicists are, and that's not because optimism is the right course of behavior, it's because the pessimists tend to leave the field. I don't think one can actually succeed in the kind of fundamental physics we do, where we are groping a bit in the dark always, without being optimistic. But we do face a pessimistic scenario, which we have to make sure to avoid. And that's based on the fact that the LHC so far has only revealed precision tests of the Standard Model, including, it appears, the Higgs sector. And so the pessimistic scenario is that the scalar particle discovered, presumably scalar at CERN, is the Standard Model Higgs to a few % precision, and that there is no direct signal for supersymmetry. There could very well be no detection of dark matter in the sky, or underground, or at the LHC. And there could be, therefore, no direct indication of the next threshold of physics, which our only clues, and again, clues only, must lie somewhere between 10 to the 10 to 10 to the 19 GeV. So this could turn out to be the case. That is extremely pessimistic and awful, because what would we do then? In this pessimistic scenario, it would be extraordinarily hard and perhaps even irresponsible to argue to build just another accelerator at 10 times current energy. And the strategy of dealing with that enormous desert, enormous range of energies until one gets to the scales where new physics, according to our present understanding, must occur, would be too large. Now, on the other hand, there's the extremely optimistic scenario, which means that the Higgs-like boson is not equal to the standard model Higgs in some way, either in branching ratios or in multiplicity of scalar particles or whatever. And luckily, that's being tested now and could very well be the case. This is a new window onto a new sector of standard theory. And then, of course, there is still, I think, a very significant chance that we will directly produce supersymmetric particles. We haven't so far, but of course, the LHC is just beginning to explore its total range of the phenomena available to it. And of course, at the same time, we are getting very close to where we might expect if dark matter is a WIMP, and it has and there's a simple explanation of why it occurs in the universe with its present abundance, that we could detect it underground or in the sky and produce it at the LHC. Any of these, and even more, all of these would provide extremely strong guidance for the next steps. And those include, of course, the ILC, which would be a wonderful complementary machine to explore the physics of the Higgs sector, but also the dark matter and or supersymmetric sector, and even larger hadron colliders. So in either case, either if you're pessimistic, which we shouldn't be at this point, or optimistic, we must fully explore the TeV to 100 TeV, for hadrons, range, because this is within the scope of what is technologically and politically probably possible. And if you're a pessimist, you better make sure that you haven't missed all the conceivable clues. And if you're an optimist, there's going to be an incredible world of fundamental physics out there waiting to be discovered in this range. So that's why the Japanese effort is so important and so welcome at this point in history, in my opinion. Now let me end by just discussing theoretical physics. Theoretical physics, I was listening to Weinberg talk about his view of particle physics. I wanted to add something to that. There are developments in purely theoretical physics based on our extraordinarily successful framework, which he described a bit, quantum field theory, which has worked so incredibly well in providing us with this standard theory, which are, I believe, are laying the basis for perhaps discovering, well, certainly new powerful tools for understanding and calculating these theories, but also conceivably, most likely, new kinds of ideas that might help us with some of these old problems. The framework of theoretical physics, as Steve described it, consisted of, well, there's quantum field theory, which is well established and works so well, and then there's string theory, which is a good idea, but nothing much has come out of it. Quantum field theory, of course, isn't a theory, it's a framework. You know, standard model isn't quantum field theory, it's based on quantum field theory. You have to assume, there's this Higgs field, a simple potential, and there are 3 gauge forces and quarks and leptons. Put a lot in to construct a theory in that framework, and most of those arbitrary elements are things we'd like to understand eventually. String theory is supposed to be a different kind of theory which explained all of that, but in my opinion, it's now turned into part of quantum field theory. There really is no difference between string theory and quantum field theory, we've learned. Neither of them are theories. They're just part of a big framework of relativistic quantum mechanics, now including quantum geometry. And the study and the advances, purely theoretical, in that domain are incredibly alive and vital and fascinating. But what this framework is, that contains the standard model as a simple example, we don't really know. But we do know that it includes not just quantum fields and particles, but extended objects like strings and branes. And it seems to contain all consistent field theories and quantum gravity. And all of this has been based on the increasing understanding of this duality between gauge theories, which underlie the standard model, and string theories, which has been revealed in the last few years, so-called ADS-CFT, which is the prime example. And that purely theoretical development is making progress, and providing us theorists with new tools and ways of calculating and understanding parts of the standard model that are alive and well on their own. They're not the energy frontier of the standard model, but rather the physics of the standard model, like the physics of QCD, which, independent of whether we're able to probe the multi-TV regime in the next century, we will be trying to understand better the nuclear force and nuclear physics for a long time. But remarkably also quantum condensed matter physics, which is, of course, described by field theory and these dualities with string theory are beginning to provide new tools for discussing very complex physics of electronic systems. And even more important from the point of view of fundamental physics, quantum gravity, which is, after all, a theoretical challenge, maybe one day connected to experiment, hard to imagine, but a definite challenge to the edifice of theoretical physics. Gravity and quantum mechanics are two of its pillars. And that is a very alive field in the quantum string framework, which is pushing us to rethink some of our basic concepts that underlie all of physics, especially space-time. Now, the standard model, or the standard theory, has many unanswered questions that as physicists, at least my kind of physicist, we're not going to be happy until we explain, like the quark mass spectrum. That's not answerable in the Standard Model or in any approach to it within the framework of quantum field theory that I know of. And that was the hope of string theory, that it would provide an explanation of the Standard Model and its many parameters. But really, not much advance has been made on that. The so-called many solutions of string theory are really many string theories within the larger framework, just as there are many quantum field theories you get by varying all those parameters in the Standard Model or the ranks of the gauge groups or whatever. We still have no idea what picks out of the kinds of consistent dynamics that are consistent with general principles in this enlarged framework, what picks out a particular theory, and what fixes the dynamics. And in a similar context, we have no idea what picks out our universe from all possible universes. These questions might be related, and that is one reason why particle physics and cosmology, quantum gravity, and quantum field theories are cannot really regard themselves as two separate efforts. And finally, space-time is under attack from many quarters. And it is such a fundamental concept that any modification of our basic ideas of what space-time is are bound to affect fundamental physics in all of its aspects. So the attacks first came from string theory, but also from just quantum gravity in general, and all of the features of space-time which we thought were sacrosanct have been eroded, leaving most of us working along those lines with a feeling that space-time and gravity are emergent concepts. But as space-time is so fundamental, it really is difficult conceptually to imagine what the right underlying formulation of our quantum mechanical version of the world is without space-time. And, but many of us think that such conceptual changes will be required and are trying to understand how that might be. They will undoubtedly affect the way we might have to think about physics at very high energy scale, or explanations of things like the hierarchy, or whatever. Our previous, more simplistic quantum field theoretic ideas might simply be discarded. And as I said, the one place where the history of space-time is most mysterious is at what's called the Big Bang, the singularity that begins the universe. That's part of the history of our universe, which is the answer to the question of constructing a theory that includes gravity, quantum theory that includes gravity. The answer to that question is the complete space-time history of the universe, not just a slice through it. And we're faced we're faced for the first time as physicists with this challenge of understanding what fixes the dynamics, picks out a specific theory on the one hand, and for the first time in asking what picks out the universe. The answer to the question of what is a theory that unifies all the forces, including gravity. And here we don't even know what the rules are. This kind of question has never been asked before. And again, that direction could very well be the thing that picks out the specific dynamics from the framework of quantum field string theory. So, we have a wonderful theory of elementary particles. The most exciting questions, including some of the last ones I asked, which were vague and deep and impossible, remain to be answered. New experiments and new accelerators, I hope, are coming very soon. And I, being an optimist, have no doubt that exciting discoveries are around the corner. So, the best is yet to come, of course. And I hope that the efforts here in Tohoku and the Tohoku Forum for Creativity will help contribute. Congratulations for starting this project, and good luck.